Welcome to section 4.2, where I explain how to do semi-classical limits using Weyl calculus and Weyl quantization. So this is the approach that is, I think, has been most successful in condensed matter physics because it is very versatile. So there are aspects to it that, for example, allow you to derive rigorous perturbation expansions, so things that have nothing to do with semiclassics. But, you know, as a nice side benefit, you can also get a very nice semiclassical limit. The central conceptual ingredient is a so-called quantization map. So it's a solution to the quantization problem. And let me be initially super vague here, and I shall become more and more specific as time goes on. But you can understand much even without knowing the explicit form of this quantization map. I call it OP, and it maps suitable functions on phase space, which is R2D, to operators on a Hilbert space. So, of course, these operators need not be bounded. So there is, of course, this is necessary so that you can quantize some of the most common operators like p squared plus v or something like that, right? For the purpose of the section, let me change notation a little bit because pseudo differential theory has its own notation, which is useful because you're dealing with lots of integrals. So what they usually do is they do not denote positions by q, but by x, y, small x, small y, and small z. And momentum. So these are just different choices. This is not a tuple. Then you have momenta, which were initially labeled p, now are psi, eta, and zeta. And these form pairs, which are points in phase space. So instead of using QP, you use capital X, which is small x and psi. You use capital Y, which is small y and eta. And then you use capital Z, which is small z and zeta. And you see why this is convenient, because you have pairs, so x and psi start with the same letter, y and eta have roughly the same shape, z and zeta again start with the same letter. So it's a very good mnemonic device, and this makes for very compact and easy to understand notation. So now this quantization map is, of course, unambiguous when it comes to position and momentum. So, for example, in position representation using microscopic units, the quantization of xj is qj, this is the position operator, and here this is epsilon xj hat. Similarly, you also have the momentum operator, which is the quantization of xij, which is nothing but minus I times the partial derivative in xj. So this is very, very easy to understand. So the idea of this first part is I'm going to fix the setting, and then I will give you the main theorem, the so-called Egorov theorem, but I will be vague intentionally, so, and then give a proof, and this proof is meant to explain to you what points need to be clarified and what needs to be proven. So in some sense, I'm front-loading the proof because the idea is very, very simple, to point out what the technical problems are that need to be solved and what needs to be clarified on a mathematical level. So the setting is as follows. So we assume that we have a pair of systems. We have a classical system and a quantum system. So the classical system is characterized by a classical Hamilton function. And this is small h. So I'm going to use small letters for objects from the classical universe. And then I'm going to use capital letters for the associated operators on the quantum level. So associated to this classical Hamiltonian, you have a quantum Hamiltonian. So this is now a Hamilton operator. And I'm going to assume, of course, that this operator is the quantization of the classical Hamilton function. So this is the link between the two systems in the description. And I'm also assuming that I have a pair of observables that comes with a classical observable again denoted with a small letter f, and a quantum observable, which is the quantization of this small f, which I denote with capital F. So the quantum observable capital F is the quantization of small f, and just like the Hamilton operator, which is one particular observable, observables need to be self-adjoint operators. Of course, if we are dealing with an unbounded operator, then we have to talk domains, etc., etc. So the discussion can become very technical, but let me avoid all these technical complications to focus on the structure first, and then we will figure out what it is that we actually have to prove. So associated to this, these two, we have classical equations of motion. So the okay, let me write it here. Of course, we can either evolve states, or we can evolve observables. Exactly. Let me just write down both. So if we look at Hamilton's equations of motion, the solution is the classical flow on phase space. And the associated ODE is nothing but x dot is equal to plus the psi gradient of h, and psi dot is minus the x gradient of h. So here, for simplicity, the magnetic field is 0. I will reintroduce it later. And of course, this translates to an equation for observables, which is equivalent. And the equation itself looks very, very simple. This is given in terms of the Poisson bracket. Let me remind you what the Poisson bracket looks like. So the Poisson bracket takes two functions, f and g, and the result is another function, and what you do is you take the gradients of both functions, and then you take the dot product. So you first take the psi gradient of f, take the dot product with the x gradient of g, and then you reverse the derivatives. And the equation here is dt f of t is equal to the Poisson bracket of the Hamiltonian with f of t. And if we specify the initial condition at time 0, that f of 0 is equal to f, then this is equivalent to setting f of t equals to f evolved composed with classical flow. So that equivalence just means if you plug this into if you take the time derivative of this guy, you obtain by computation the right hand side, or if you look at the solution to this, then you find out that the unique solution to this equation is given by this here. So this gives you an equation of motion for observables. And now let's look at the corresponding quantum evolution. Of course, this is the evolution for quantum observables. And also here we have an explicit expression for the solution in terms of the unitary evolution group. So here the time derivative of the time evolved observable is I divided by epsilon times the commutator of the Hamiltonian with f of t. And again, if we impose the initial condition at time 0, then this is equivalent to the solution that f of t is given by e to the I t divided by epsilon h times f times e to the minus I t divided by epsilon h. So you conjugate with the unitary evolution group. This is very easy to understand, and you see that conceptually speaking, the Poisson bracket and I divided by epsilon times the commutator play the same role, and this will become even more explicit in the pseudo proof that I'm going to give next. So now what we would like to do is we would like to compare the quantum mechanically evolved observable and let me give you a different name that makes it more explicit. So let me call this FQM of t, but this is identical to f of t, which is just this here by definition. Let's compare this quantum mechanically evolved observable to the quantization of the classically evolved observable. And how is this defined? Well, let me call it FCL for classical. This is just our quantization, whatever that may be at this point, of f of t. And because this here is an operator on a Hilbert space and this here is an operator on a Hilbert space, obviously, you can compare the two and you can find out whether they are approximately equal to one another or not. So of course our Hilbert space in the standard position representation is just L2 over RD. So now let me give you the main result of this section. Well, the vague version, what I call the vague version. So it's maybe you can regard it as a pseudo theorem. And it is a pseudo theorem because I will cheat and say under suitable conditions on small h and small f, the following holds. For any positive t, constant t, we have that the difference between the quantum observable and the classical observable in operator norm is equal to order epsilon times the absolute value of t for all t from the interval minus capital T to plus capital T. So just a small comment on the time scale of validity. So you're comparing a linear evolution to an, in most cases, nonlinear evolution. So that means that the proof of the Egorov theorem at one point will implicitly or explicitly rely on something like the Grönvall lemma. And the timescale of validity of the Grönvall lemma, at least in simple versions, is just like this here. So you just have a fixed time t, which is independent of epsilon. That's the key point. So that this estimate here holds true. With some technical effort, you can also prove Egorov type theorems on the so-called Ehrenfest timescale, where you gain a logarithm, which is the best you can do if you have to, if the only thing that you can use is the Grönvall lemma, if you don't have any additional knowledge on the Hamiltonian or the observable. So pseudo theorem requires a pseudo proof, but please don't take the proof as something that you need to completely understand, but more as something that helps us or tells us what our homework is, what we have to clarify. So the first step in the proof is a so-called Duhamel argument. And okay, I'm using the term of art on purpose so that you know it. But if you don't know what a Duhamel argument is, well, it's better known as the fundamental theorem of calculus. A fancy version, but essentially it's that. What does that mean? Well, we will write a function as the integral of its derivative. So the function that we're concerned with is this here. And what I would like is a function whose integral of the derivative is equal to fqm minus fcl. And let me just give you the solution, which is straightforward, and then we can just check it together to be sure that I didn't do anything reckless here. So it's the integral from 0 to t. Then I have to take the derivative. So remember, that means that whatever is here needs to be evaluated at t, and then you subtract this function evaluated at 0. So whatever is here evaluated at t should give you the quantum time evolution. And if you evaluate at s equals to 0, then you should get the classical time evolution. And the way you do this is you take e to the is divided by epsilon h. Then you take f classical at t minus s, and then e to the minus I s divided by epsilon h. So let's check if this is correct. Okay, if we set s equals to t, then this gives us e to the plus it divided by epsilon h. Okay, that's good. If I set s equals to t, I have f classical evaluated at 0. Okay, f classical evaluated at 0 is the quantization of small f at 0. And because phi evaluated at t equals to 0 is the identity, you can view the classical flow as a group representation. So phi 0 is the identity, so f of 0 is just f. So you get the quantum time evolution, and for s equals to 0, well, this becomes the identity. This is also a fancy way to write the identity. And f classical evaluated at t minus 0 is f classical. Okay, I have a very obvious typo here. Sorry about that, I didn't notice. And okay, just like that, we've rewritten this difference as the integral of a derivative. And now what we can do is we can simply evaluate the time derivative. And then integrate, and then estimate the expression that we obtain. Okay, so the first term that we get is plus I divided by epsilon h times e to the plus I s divided by epsilon h. Now let me just write out f classical. So that's the quantization of f of t minus s e to the minus I s divided by epsilon h. Okay, then I have a second term where the time derivative acts on this guy here. Of course, I'm assuming I can just exchange the application of vectors with the s derivative, that I can exchange the s derivative with the quantization map and so forth. So if you do this rigorously, all of this needs to be justified appropriately. But again, this is a pseudo proof. We don't actually have to worry about these things at this stage. So let me just write out all of the terms that I get first. And then let's look for simplifications. So when we derive the last term here, then we get the same, almost the same thing as when we derive the first term. Just that now we get an additional minus sign. So now let's hunt for simplifications. One is that we may, of course, commute H with its unitary evolution group. So if H is a self-adjoint operator, which was our assumption, then according to functional calculus, these two guys commute. Then here, well, we have the S derivative, but because the argument is t minus s, we can also think of it as minus the t derivative of f evaluated at t minus s. And this here is, because this is the time evolution that we're interested in, is minus the Poisson bracket of h with f of t minus s. So now we can collect, and also we can collect these two terms with one another, and we get a commutator. So what we get is the integral from 0 to t ds. And now we can factor out e to the plus is divided by epsilon h on the left side. Then I have I divided by epsilon, the commutator of op h, which is capital H, and op of f of t minus s minus the quantization of the Poisson bracket of h with f of t minus s. And then on the right, we have factored out the unitary evolution group. Okay, so this is step one. So now we've just used the fundamental theorem of calculus. And what we can do is we can just take the operator norm on both sides. So on of course, we are pulling the norm into the integral. So fqm of t, the operator norm of fqm of t minus f classical of t. This is less than or equal to, if we look here, well, we can take the integral time, the absolute value of the integral times the maximum of the integrand and okay, what is the integrand? Let me copy and paste. So I have a norm here, a norm here. But now the quantum evolution is unitary, so I can just kill it. And what remains is Well, and of course, this here is absolute value of t. So this is equal to t times the maximum of, well, the bit in parentheses. And the assumption now is, well, not the assumption, that is the claim of the theorem. The claim is that the right-hand side is order epsilon times absolute value of t. So it's already very suggestive where the absolute value of t comes from, so I will not dwell upon this any further. And the central part of, or one of the things that we need to figure out is that this here is indeed equal to order epsilon. So let me summarize this. And this summary should serve as our homework assignment for the rest of the chapter. So first, we have to define and characterize the quantization map. And second, we have to prove that I divided by epsilon of the commutator of op h and op f of t minus s minus the quantization of the Poisson bracket of small h with small f evaluated at t minus s, that this here is order epsilon small. And of course, implied in all of this is that we, of course, need to cross our t's and dot all the i's. For example, that even when op applied to f at time 0 makes perfect sense, we have to make sure that the time evolved classical observable is still quantizable, and so forth and so forth. But this will be part and parcel of, for example, this part here. All right, and with that, part 1 is over, and the following parts are then mainly about filling in the gaps in the arguments.